started. We have a little bit after, a couple minutes after, so I think we're good to go. We have a few people filtered in. So welcome to the Inspire Me Mechanical Engineering Seminar this week. We are, I do want to, before we get started, I want to remind everybody, make sure you sign up on our sign-up sheet there. We have to pay for the cookies, and so there's like a, what the note is here, and so anyway, if you want cookies in the future, you got to do that. All right, so we're really excited today to have our speaker, our guest speaker is all the way from Idaho National Laboratories out in eastern Idaho. So we're very excited to continue this partnership of sharing their work with us like we did last fall, and so that's where we are today. So our speaker is Dr. David Hurley, who is a directorate fellow at the Idaho National Laboratory. So he's going to be here talking about this probing materials with lasers. So we have a lot of MSc people here. I can see that hopefully have a lot of interesting questions at the end. So basically, he received a PhD in material science and engineering from Johns Hopkins University, and he also has degrees in physics and mechanical engineering, so he covers a lot of those bases, and it's kind of a combination or a little nexus of the work that he's doing now is really related to all those different fields, and so it's kind of an interesting combination. And so his group currently at INL is contributing significantly to the foundation of a new field of mechanical characterization that's termed laser resonant ultrasonic spectroscopy. And so he's also served as the experimental coordinator and executive board member for the Center for Materials Science and Nuclear Fuels. So a lot of it, obviously, with INL is associated with nuclear industry. So without further ado, I'm going to go ahead and let's welcome our speaker, Dr. Hurley.
Well, thanks for the introduction, Bill. So I'm Dave Hurley. I'm in the Department of Material Science and Engineering at Idaho National Lab. And like Don said, I'm going to talk to you today about how we probe material properties in microstructure using lasers. Before I get started, let me just talk a little bit about INL in case some of you aren't familiar with it. It was a laboratory established in 1949. It was first called the National Reactor Testing Station. So it developed a lot of different reactors over its life. It's 52 reactors altogether. Some of the more notable reactors are Experimental Breeder Reactor 1, which was the first reactor to generate usable electricity. It powered ARCO. And it's actually been decommissioned. You could go there and look at it. It stands out in the desert. It's kind of fun to go to. We also have the first naval propulsion nuclear reactor, and that was also constructed out in the desert. So we have a strong footprint in all things nuclear. Our landlord at Department of Energy is the Office of Nuclear Energy. But in addition to nuclear energy, we also have footprints in national security research and energy security and sustainability. So we're doing research in things like grid reliability, how to integrate renewables into the grid. We also have a small research group that looks at advanced vehicle technology. So we're doing a lot of different things. Our primary focus is nuclear energy. So that's the lab. Let me give you kind of motivation for what I'm going to talk about today. And this is a micrograph of a nuclear fuel pellet. So essentially what we have here is we have the fuel meat, which is in the interior, and then we have the cladding. Having problems here. Okay. And so these pie slices are sections of the fuel that are taken out of the fuel at different stages of burnup. Okay? And so it looks quite ugly, and there's a good reason why it looks ugly, because when uranium fissions, it creates a lot of neutrons, and these neutrons are speeding through the material, and they're creating all kinds of defects. So the idea is, first of all, I want to ask, how many people here have a background in material science? Raise your hands. And how about just only in the... Okay, well that makes it difficult. So, okay, so just a little bit for the ME people. You know, nuclear fuel, it's uranium oxide typically. We also look at metal fuels, but the atoms are arranged, it's a crystalline material, so they're arranged in a certain order. And so these energetic neutrons disrupt that order. They create defects. And those defects really influence the way the material behaves. Okay, so the industry is interested in three things. They're interested in creating fuel that has a higher burnup. That means you can keep it in a reactor for a longer time. They're interested in producing fuel that is less prone to premature failure. A lot of times a fuel assembly will have a burst and they'll have to shut down the plant and take out the bad actor. Shutting down plants is really expensive. We're talking millions of dollars a day. And of course that cost is passed on to you, the consumer. And they're also interested in coming up with fuel that is tolerant to severe accidents. So like, think Fukushima, 3 Mile Island, things like that. So from a material science point of view, if you look at these three things, really at the fundamental material science level, they're related to two things. One is thermal conductivity. So if we could have fuel that has a higher thermal conductivity, it would be less prone to severe accidents like Fukushima. Fuel typically is inherently a poor thermal conductor. It starts off with a conductivity of about 10, and over its lifetime that decreases to about 1 watt per meter degree Kelvin. So that's one thing, thermal conductivity. The other thing is related to chemical transport. So as the uranium fissions, it creates what's called fission gas. It's typically xenon. And these fission gas bubbles coalesce, and eventually they migrate to this little section here between the fuel meat and the cladding is called the plenum. And over time, it starts to build pressure, and that causes the fuel to fail. So there's two things: thermal transport, chemical transport. They're both strong functions of microstructure. So that's that. So I had about 8 years ago a program director come up to me and said, Dave, can you measure microstructure of fuel? Can you measure material properties? Can you relate the two? And also, can you do this in pile? And so that's a lot of boxes to check. And so, you know, it's a fuel, when it comes out of a reactor, it looks like this up here. It's all cracked, and when you cut open the can, it's basically just little shards. And so for you ME folks, you can think of trying to make a dog bone specimen to measure the mechanical properties. That would be really difficult for a shard of nuclear fuel. So we have to come up with kind of unique ways to measure material properties, unique ways to measure microstructure, and then maybe potentially install these in a reactor while the fuel is cooking. So, so we came up with a number of approaches. The first one I'm going to talk about is laser ultrasound. And so I'll talk about two broad areas there. The first is using laser ultrasound to measure corrosion film thickness. And the second is using laser ultrasound to measure changes in texture. Okay, so without further ado, and so I call this section of my talk the large scale. So we're looking at larger samples, they're millimeters to centimeters in size. And so what is laser ultrasound? Well, are you familiar with ultrasonics? Okay, well, ultrasonics typically, they're just mechanical waves in material. And they propagate at acoustic velocities. So you have a mechanical wave that is going like this. It's a longitudinal wave, or a wave that's moving like this. It's called a shear wave. The velocities in aluminum, for instance, is about 6,000 meters per second. So that's what a mechanical wave is. You can use it to interrogate a material. The particular brand of ultrasonics that we're using is called laser ultrasound. And so what we do is we take a sample, like my phone, for instance, and we shine a laser on it, and it's a pulse laser. And so a portion of that energy is absorbed by the sample, and it's quickly converted into heat. And so you have this really sharp thermal gradient, and due to the action of thermal expansion, it serves to launch acoustic waves. These are fairly high frequency acoustic waves, up to about 100 megahertz. And so you can do laser ultrasound in the time domain. And that's what I have here. So this is generating here, and this is detecting on the other side. And the first thing you see come through the first disturbance is the longitudinal wave, and the second disturbance is the shear wave. And so some easy things you can do with this is from these two measurements, you can calculate both elastic constants if it's an isotropic material. So that's the time domain. In the frequency domain, we do something kind of similar to hitting a drum head with a drumstick. And so if you hit a drum, you hit it right in the middle of the drum head, you'll see it vibrate at its fundamental mode. We want to excite all the modes because there's a lot more information if we can excite all the modes. So if you take a drum head and you hit it near the exterior of the drum head, it won't make a pure sound. And the reason is because you're exciting all the higher harmonics. And that's what we want to do. So for a frequency domain experiment, typically we excite here and we measure the way down. So I'm going to talk more about both of these techniques in the next few slides. Okay, so the motivation for measuring corrosion. So you remember that picture, we had the fuel can, which is zirconium, some kind of zirconium alloy, zircaloy, and the interior is the fuel meat. Well, the exterior of that can is exposed to high temperature wire and steam, and so it corrodes, and it can corrode rather significantly. And so one of the things the regulators want to know is, can we measure the thickness of that corrosion film? And the thickness of the corrosion film is somewhere on the order of, it starts out a few microns all the way up to about 20 microns. So, and I don't have a picture of the film. So this would be the film right here. And this is a cartoon, but this is a film that's about maybe 10 microns thick or so. And so what naturally comes to mind is, can we use laser ultrasound and pulse echo to measure the thickness of the film? And the idea is that you generate a high frequency longitudinal wave and measure the time it takes to reverberate back to the detector. But it turns out at 20 microns with conventional laser ultrasound, we just don't have the bandwidth to do that. We would need something in the order of about 5 gigahertz. And so we don't have the bandwidth to do that. So what we're doing instead is we generate ultrasound that propagates on the surface of the material. So it's called a surface acoustic wave. And so it's the exact same wave that you get in an earthquake. Actually, the mathematics is exactly the same. And these are waves that are confined to propagate on the surface of the material. And because they're propagating on the surface, they're sampling the oxide layer continually as they propagate. And as a result, they're very sensitive to that oxide layer. So, so if you take you look at a Rayleigh wave or a surface wave on a pristine surface, you send in a pulse like a delta function. That delta function will propagate forever and it'll continue to look like a delta function. As soon as you add a layer to it, you get something called frequency-dependent dispersion. That means different frequencies that compose that delta function travel at different velocities. And so what that means is that the pulse starts to spread out. And that spreading, or that dispersive power, is a strong function of the film thickness. So what we do is, it's kind of neat. We take a pulse laser right here, break it into two, and then we interfere the two components of the pulse laser on the sample. And that sets up a interference gradient shown here. And so that allows us to generate narrowband surface acoustic waves. I mean, because we have this inherently broadband pulse laser source. So this is one way to put all that energy at a single frequency. And so the acoustic wavelength in this case is related to the gradient spacing. So we can create these narrowband surface acoustic waves, measure the velocity, and then we get 1 point on this graph, velocity versus wavelength or wave vector. And so we can change the wavelength by changing the angle at which the two beams intersect, changing the frequency to the same measurement, and we can build up this dispersion relationship 1 point at a time. And then through some fancy mathematics, we do the inverse problem where we calculate the film thickness. So it's It sounds complicated, and it is, but the nice thing is you can do it remotely. You don't have to touch the sample. Those are characteristics that are really important for doing measurements on nuclear fuel. Okay. So the next thing I want to talk about is something we kind of developed at our lab. It's called laser resonant ultrasound spectroscopy. And this is, I think, something that the ME students will find interesting. You've all heard of beams bending, right? Well, this is like a beam bending, but it doesn't have a supported surface, so it's not attached to anything. It's a freestanding beam, and we cause it to wiggle in all kinds of different directions. But it's analogous to a Timoshenko beam, if you will. And so what we do is we take a sample with known geometry, and we ping it with a laser, and then with another laser, we measure the ring down. And so then we take the Fourier transform, and we get the resonant spectrum. Right? And the lowest peak would be the thing that's related to kind of the Timoshenko beam theory for a non-suspended beam. Okay, and these higher orders are just higher order. They come out of the elastodynamic calculations for the beam, pretty straightforward. But so that's one experiment. Now what we do is we take our laser and we move it to another location that's represented right here. Do the same experiment, measure the ring down, and what we do is we get a different frequency spectrum. I mean, the peaks are located in the same place, but their amplitudes, relative amplitudes, are different. So if we take one peak, for instance, and measure its amplitude as a function of scan position, we can get out the eigenmode, or what the vibrational shape of the beam looks like when it's vibrating. And so we can, for instance, window the spectrum to look at the mode at 63 kilohertz. We do the same experiment where we're windowing at 393 kilohertz, and so we get different mode shapes. And these mode shapes are related to the elastic properties of the material. Okay, so now Rust, which has been around for a long time, typically what they do is they use this to do the inverse problem. So we can calculate this in a very straightforward way. And the inverse problem essentially involves doing the forward problem several times so that you minimize the error between your calculated spectrum and your measured spectrum. And it's a way to measure the elastic constants of the material. It's prone to some error, and the reason because typically it's done where you take a sample, and this is without using lasers. You take a sample and you excite it with a piezoelectric transducer, and here you measure its ring down with another piezoelectric transducer. And so experimentally, all you have access to is the frequency spectrum. So you kind of have to guess that this is, a torsional mode at 393 kilohertz. You have really no idea of knowing, but by measuring the shape of these vibrational frequencies or the eigenmodes, we can identify the peaks, and so we can more accurately do the inverse problem. Okay, so how do you measure microstructure with it? Okay, so again, this is where it gets difficult talking to mechanical engineers and material scientists. So I'm just going to talk to mechanical engineers right now. We have a sample here that's that's polycrystalline copper. And so what that means is that you have copper as a crystalline material, so all the atoms are arranged in a certain way, but that volume only extends so far, and then you get another region where the atoms are also arranged almost perfectly, but the orientation is different. And so these regions where they're arranged almost perfectly are called grains. And so what we have here is it's called an electron backscatter micrograph, but it's showing you the orientation of these grains in false color. So a red grain might be oriented like this, a green grain like this. And so it's information you get from a scanning electron microscope, and it's very useful. So what we're doing here is kind of a proof of principle experiment where we're saying, can we measure grain microstructure? Can we measure texture? Can we do it in situ at high temperatures? And so we take polycrystalline copper, we roll it, and we create this very fairly well-defined rolling texture. and then we heat it up, and we have this extremely well-defined recrystallization texture. If this was all red, which it is almost, it would be a single crystal. So this is something that mechanical engineers probably don't realize, but the elastic constants of a material are a strong function of texture. So the elastic constants for this sample are going to be profoundly different than they are for this sample. Okay, so what we do is we do our experiment as we heat this up. So we ping our sample while it's in a furnace, and we measure. We're measuring this mode right here, for instance. And so what we see is that the mode frequency starts to decrease. That's because the elastic constants are a function of temperature. But then you see this really stark transition here, a little above 200 degrees C, and that's due to the recrystallization transformation. And it takes place quite rapidly. So the answer to the question is yes, we can use laser ultrasound to measure microstructure evolution. Potentially we could do this in pile. Recrystallization, well, that was a tough one. It turns out I was lucky on that. All fuel recrystallizes. For recrystallization, all you need are two things. You need dislocations, and you need high temperature, and in a nuclear fuel you have a bunch of both. So that's a pretty easy thing. The one thing I didn't realize is that this is an incredibly hard thing to model. So that was another box. He said, okay, I want you to do all this, and I want you to provide a validation metric for people doing computational material science. Well, that's something I didn't think about. And the reason it's hard to model is, well, so the basic model would just be using a phase field simulation to basically model, go from this state to this state. But the input to the phase field simulation requires dislocation density. And that's a tough thing to do. People have suggested doing discrete dislocation dynamics. That doesn't work for this kind of dislocation densities we have here. Really high. Another model would be polycrystalline plasticity. That doesn't give you enough detail to actually accurately do the phase field simulation. So we're working on that right now. Let's see, how much time do we have? 13 minutes?
We generally go.
I'm good.
Okay, you got
Yeah.
some time.
All right, great.
So 12:45 or so, and have some questions.
So I won't talk about this. I'll save that for later. But so this is kind of brings me to the end of this section. Does anyone have any questions about kind of what laser ultrasound can be used for, or like the sample dimensions? Did I tell you about that? How big they are? Okay, great. There'll be a quiz after this. Okay, so the second segment of my talk is called Smallscale. And I wasn't really sure who was going to be in attendance. I knew mechanical engineers were going to be here, some people from material science, and I know a lot of your departments are interdisciplinary. So I tried to kind of put together samplings of a lot of our work that might gain some traction here and there. At any rate, this section is kind of jumbled. That was done on purpose, so I'm going to talk about a lot of different things. Some of these things only have loose application to nuclear energy, and you'll see that. But hopefully it'll get you guys thinking. So the first thing I want to talk about is measuring thermal properties. And this is kind of similar work that Jan Leon is doing in his lab. We use lasers to do it. Our first example was laser ultrasound, where we have a pulse laser and a laser interferometer for doing generation and detection. In this case, we have a CW laser for exciting thermal waves. And so the idea is that can we measure the thermal conductivity, and can we relate that to microstructure? And so the methodology is pretty simple. We have this CW laser, it's on all the time. We amplitude modulate it, so we turn it on and off at a certain frequency. And we use it to heat a sample, and that's the red arrow there. And then with another laser, we measure the temperature. So the second laser is a thermometer. And the way it works is it measures small temperature-induced changes in reflectivity. So that's our thermometer. I mean, you think of a thermometer filled with We're looking at the height of the mercury column and saying, oh, I'm reading the temperature. You're really not. You're just reading thermal expansion. In this case, our thermometer is reading changes in reflectivity and temperature. So that's our thermometer. That's our heat source. So the thermometer would see the heat underneath the source going up and down sinusoidally, but it would be slightly out of phase. And the reason it's slightly out of phase is it takes a while for the thermal energy to propagate there. And then as you start to move the thermometer further and further away from the heat source, you'll see that phase difference increases. And that phase difference is related to the thermal diffusivity of a material. So by measuring that phase difference, we can back out the thermal properties of the material. Since we're using lasers, we can do experiments where the lasers are very tightly focused, so we can look at thermal properties on a very, very small length scale. Some of our experiments have looked at thermal properties of small precipitates in metal matrix, for instance. We can also use this approach to measure something called thermal anisotropy. In single crystals, in some single crystals, the thermal properties aren't the same in all directions. Quartz is an example. Thermal properties are quite different in one direction in quartz than they are in the X2 direction. And so what we're doing here is just doing a kind of a full field image of this approach in 3 dimensions. And so this is the thermal wave phase profile that I talked about earlier in the full field image of the thermal wave phase profile. And so what we have over here is basically a profile along the X1 direction and the X2 direction. And the slope is linear. The slope is a function of essentially the thermal property of the material. And you can see the slope in the 2 directions is different. So it gives you a clear indication of the thermal anisotropy of the material. And you can do it, again, on pretty small length scales. This is a box here, but it's a micron. So it's 46 microns. Okay, so what can we use it for? Let's try to relate this back to nuclear energy. So one thing we wanted to do, and this was, as Don alluded to earlier, part of the Center for Material Science and Nuclear Fuel, that it was a DOE center tasked with trying to measure thermal conductivity of nuclear fuel and relate it to microstructure. I mentioned that the fuel conductivity goes down over time. It's due to the deterioration of the microstructure. So there's 2 types of microstructure that we're going to talk about here. Again, for the mechanical engineers, one microstructural feature is a point defect. So an atom that's missing, for instance, or a foreign atom that's where it shouldn't be. Those are called point defects. And the other feature is a grain boundary. So again, those are where the atoms are all lined up in a row, and then you reach a boundary where it has a different orientation. So both of those things can influence thermal transport. And we're going to try to do a really slick experiment where we have what's called a single effect study experiment. So we measure only the influence of point defects or only the influence of grain boundaries. And we didn't do that. We got a sample that had an abundance of grain boundaries and an abundance of point defects. So in an effort to try to make lemonade out of lemons, we did measurements anyway. And what we found out is something really interesting. We found out that there's a cooperative effect going on between the point defects and the grain boundaries. And the behavior of this material is different than if you made separate effect studies only on grain boundaries or only on point defects and then added those 2 things together. And so what's going on is the grain boundaries are, they're high energy areas, and they like to suck point defects, bring them to the grain boundary. So they're a sink for point defects. And that has 2 things happen when you look at it from a thermal transport point of view. One is that the grain boundary contact resistance, or the grain boundary resistance, is going up. But the conductivity of the grain interior is also going up. And they don't do it in such a way that they counteract each other. They do it in such a way that the overall conductivity of the material increases. So you get this cooperative effect that we wouldn't have noticed unless we had a really crappy material. So it's kind of nice. If you don't get what you want, keep on trying. You might find something interesting.
Okay, so this is a similar experiment. So the idea was, and this was a sample given to us by Sandia, can we measure thermal transport across a single grain boundary? And since we have these highly focused probes, we thought we had a pretty good chance of doing that. And so this is a silicon bicrystal made for us by Sandia, and this is an electron backscatter micrograph of the sample. It turns out that we do everything optically, so we're imaging the surface optically. We can't see defects, so we have to either put down traditional marks or use conveniently placed defects to find out where we are on the surface. We happen to have two really nice defects right here, so we could always go to those and find out where the boundary was. So we heat the sample, and then with our probe, we measure the heat transport across the sample. And in this case, we see this temperature discontinuity at the sample surface. And so that allows us to measure something called the Kapitsa resistance. We got a rather large Kapitsa resistance. We weren't really sure why until we went and cut up the sample and did some high-resolution TEM and EELs. And what we noticed is that the folks at Sandia weren't as good as they claimed to be. There's almost a native oxide layer here at the interface between the two silicon crystals. And so that contributed substantially to the interface resistance. The nice thing about this experiment is that it provides a one-to-one correspondence between what we can measure and what people can model. So a lot of times when people do models, they have to upscale through several orders of magnitude. In this case, there's no wiggle room. It's what we measure is what they model. And so a group at Florida modeled this, and they got very nice results that compare very closely to what we measured. So we're happy about that. Although their paper seems to be getting referenced more often than ours. So. Okay, great. So that's I'm down with two methodologies. The third methodology that I want to talk about is something that involves an ultrafast laser. And so an ultrafast laser, the one we have in our lab, has a pulse length of about 100 femtoseconds. So if you equate that to frequency, that's about 10 terahertz. So that's way past anything we can do with electronics nowadays. So we have to use this special technique called pump probe. So the pump probe technique is pretty slick. You take this 100 femtosecond pulse and you cut it in two, and you call one the pump and the other the probe. And the idea is that the pump, you send it to the sample and you create some kind of disturbance. And then with a time delay probe, you come in and you measure that disturbance at one point in time, because essentially the laser pulse looks like a delta function, right? And then you send it to a photodetector, and you repeat that experiment several millions of times. And so now you have information at one point in time. If you want to scan time, what you do is you delay your probe even more by having it propagate a longer pathway. And then you measure at another point in time. And so to put this in perspective, light travels about 1 foot per nanosecond. So if you want to scan 1 nanosecond of time, you have to have a delay stage that can move 1 foot. So that's the pump probe method. So what we used it for is, again, to look at silicon. And this is kind of funny. When we first started the Center for Material Science and Nuclear Fuel, they said, we need to come up with surrogates for uranium oxide until we get permission to start using uranium oxide in our lab. And I'm like, well, if I'm going to come up with a surrogate for uranium oxide, I want to come up with something that has similar optical properties. And uranium oxide is a semiconductor. And so I picked silicon. And I remember our director is like, silicon, really? You know, like, why don't you pick cerium oxide, something else? But no, I picked silicon. And it turned out I was pretty fortunate because it does behave optically very similarly to uranium oxide. And so this first experiment is just to kind of see what happens when we hit silicon with these femtosecond pulses and measure kind of the evolution of the disturbance. So what we're doing is we're exciting the silicon with above band gap energy, so 400 nanometer pump plate. What that does is it photoexcites electrons into the conduction band. And we're probing with 800 nanometer light. So normally the silicon is transparent to the 800 nanometer light, but because you suddenly pump all these electrons up into the conduction band, it behaves like metal. And so we see a huge change in reflectivity. And that's just due to these photoexcited electrons. And they start to diffuse out, and after a while we're left with this steady state term that doesn't change with time. And this was really strange. We couldn't figure out what was going on. Finally, we figured out this is a thermal wave. Okay, and it's at, like 100 kilohertz frequencies, so it's very slow compared to what we're looking at. So it's almost static. The thing that was curious is why did this plasma wave, or why did the electron contribution vanish so quickly? It vanishes in about 100 picoseconds. We first thought it's because they were diffusing out of our interrogation volume, but we quickly did some calculations and we figured out that couldn't be the case. And so what's happening is actually these electrons are recombining very, very quickly. And they're recombining at Shockley-Reed Hall recombination centers. What's happening is the sample was mechanically polished, and so there's a lot of damage, and so we could get very fast recombination. So we can measure thermal properties, we can measure recombination time, and it's kind of neat how we did that. We have a thermal wave component and this diffusing electron gas component. They happen to have opposite polarity, so you get this, if you look at the amplitude of the lock-in, you get this very funny shape. And if you measure the amplitude of the electron plasma as a function of time, you'll see that it drops off like this. And so we can use that to measure the recombination time. We also did some experiments where we changed the fluence. And what that does is, as we pump this harder, that moves the recombination time to the right and increases the recombination time. And the reason for that is that we have this really dense electron plasma, and it's starting to screen these recombination centers. And so we can also identify not only the recombination time, but the recombination path. And finally, we did one other experiment where we pumped it really, really hard, and we heated up the sample such that we were causing these defects to anneal. So we could see this real-time annealing of the defects just by monitoring the recombination time. So just with one simple experiment, you can measure a lot of different things: thermal properties, you can measure recombination time, pathway, you can also sensitive to annealing of defects. Okay, so that was an introduction to the pump probe method, and I'll wind down here shortly. So these next two slides are using the same technique, pump probe, but instead of generating heat or generating electrons, here we're generating very high frequency acoustic waves. Sometimes they're called phonons. The generation mechanism is very similar to what I talked about before with laser ultrasound. So you have a pulse laser. In this case, it's 100 femtoseconds long, and it creates this very short phonon pulse or acoustic pulse that propagates into the sample. The detection is kind of slick. Our probe detects a portion of it, reflects off the front surface of the sample, and another portion reflects off the propagating phonon pulse. So it sets up this interference pattern. And the interference, the frequency of that pattern is related to the acoustic velocity. So we did an experiment. I realized I don't have, well, this is the surface. So we did an experiment where we generate here, and so we're generating both the coaxial generation and detection. And we get these things, I don't know if I mentioned, they're called Brillouin oscillations. And originally at this first position, which is S1, I think, we only have one oscillation frequency. And as we start to scan the sample, we see a second oscillation frequency show up right here. And that's due to the fact that this acoustic wave is propagating into grain B, and the acoustic velocity is different in grain B than it is in grain A because they have different orientations. So to make a long story short, we can kind of use this approach to map out the structure of the grain subsurface. So it's a way to look underneath the sample. So you're familiar with those electron backscatter micrographs? They're only looking at the surface. This approach allows us to look below the surface using a relatively inexpensive method to do that with. So subsequent to our ultrasonic measurements, we took a fib lamella of this uranium oxide sample, lifted it out, and did EBSD. The results were very, very close to what we measured. So what we're looking at now is, this is only the longitudinal velocity, I mean the longitudinal mode. We also can generate both shear modes, and by looking at the velocity of all three modes and the relative amplitude, the question is, can we use that to extract the grain orientation? So then it would be really a true three-dimensional electron backscatter approach, or giving information equivalent to 3D electron backscatter. Okay, so this is, I think, the last thing I want to talk about, and this is just kind of fun. So it's using the same pump pulse, pump probe method to generate surface acoustic waves. So I said before, these are very similar to earthquake waves, but they're on a very, very small scale. And so what happens when you throw a rock into a pebble, or a pebble into a pond? You see these wave fronts that go out and they're circular, right? Well, water is elastically isotropic. Single crystals are elastically anisotropic. So the acoustic velocity varies as a function of direction. If you look at it from a stress strain point of view, you impose a certain stress in one direction, you get a certain displacement. In a different direction, you get a different displacement. So it's referred to as elastic anisotropy. So these are surface acoustic waves in single crystal copper. And so this is the surface acoustic wave right here, and this is what's called the surface skimming bulk wave. So this is the wave that arrives first in an earthquake. It doesn't cause a lot of damage. It's the surface wave that causes all the damage. And single crystals, in addition to these really funky shapes, you also get different amplitudes depending on which way you're looking, even though the source is isotropic. And that's because the phonons, or the acoustic waves, are focused along certain channels. It's referred to as phonon focusing. So we did the same experiment in our texture copper sample with the idea that can we measure local texture using this approach? And yeah, just about done. And so these are our results. I was kind of surprised that we were able to do this, but we got results that matched our very simplistic model. The model is really, all we're doing is an angular spectrum of plane waves, but we get wavefront shapes that look very, very similar. So I think there's some hope of actually measuring texture using this approach on a very, very small length scale. Here it's only 140 microns. So I have other stuff to talk about, but I think I've kind of saturated you guys. So I'm going to just go ahead and thank you for your time and ask you if you have any questions.
Yeah. Very nice talk. Question on your pump probe for your silicon.
Uh-huh.
And you mentioned that you had ground the wafer down
Right.
to cause damage.
Uh-huh.
And then you said those were causing deep levels and very fast decomposition.
Right.
One way to get rid of the damage is to etch.
Right.
And did you try that to see if you could get rid of the deep levels to see if the decomposition?
Well, it's a really good question. It turns out what we were interested in was measuring the thermal wave across the silicon bicrystal. And so what I showed you was kind of our results well removed from the bicrystal membrane. And the fact that plasma wave decayed so quickly, because we weren't interested in that, but it was by far the biggest contributor to the signal. So we were happy that it decayed quickly. But you're right. I mean, if we're interested in the defects and how to get rid of them, we can use this approach to study that. But no, so we never thought of etching.
Very interesting.
Yeah.
So for the laser ultrasound, you're talking about, one of the boxes they wanted you to check was to be able to do it in pile.
Mhm.
So I assume that would mean you have fiber couplets. What, are these ultrafast pulses? And then would you have to worry about dispersion?
Really good question. So so there's two answers to that. No, they're not ultra-fast pulses. They're 10 nanosecond pulses, so dispersion is not going to be a problem. We would want to fiber couple them. Unfortunately, fiber is darkened in a high gamma environment, so we're trying to come up with new fibers that would be radiation tolerant. But that's interesting you bring up the whole pulse dispersion. Even for the picosecond stuff, we don't have to worry about our 150-second pulse dispersing because we're generating relatively low-frequency acoustic waves. The acoustic bandwidth is related to the acoustic transit time across the absorption volume. So we can even use picosecond pulses. So that's a good question. Yeah.
So in the latter part of your talk, you talked about having imaging subsurface grain boundaries, essentially. What's I guess, maybe I didn't catch it, what's your penetration depth, and then I guess a couple questions. What's penetration depth? Can you couple it with EBSD to create a volume to map your surface and your structure underneath, and then what's the influence of, say, like an oxide, a native or grown oxide?
Okay, so the penetration depth, the ultrasound will go a long ways in. I think the penetration depth is really related to the fact that our probe, in order to be sensitive to these Brightline oscillations, you have to have a probe that's tuned close to the band gap. And so, if you look at the Brightline oscillations, they decay over time. It's just because of optical absorption of your probe. Does that make sense? Yeah. So I think that's really what's going to limit how far we can look. The other thing is that the ultrasound we're treating it as propagating like a cylinder, but it's not. It's diffracting. And that's part of the modeling that we haven't really taken into consideration. So coupling it with the EBSD, what do you mean by that?
Well, I know there's efforts that, destructive efforts, I guess, to if you could model a few grains deep.
Right.
I know each interface is going to cause its own separate.
So you mean like not doing EBSD on the surface and then not doing the serial sectioning that they typically do, using this to look below the surface?
Yeah.
Yeah, I think that would be really appealing.
Then you have to worry about an oxide phase.
Oh, that's the...
I mean, I know you specifically addressed that in another technique, but if you try to couple these two together.
Well, so are you talking an oxide on a metal?
Yeah.
Okay, so it won't work for a metal. But it has to be semi-transparent, so your probe has to be able to look underneath the surface. So it typically only works for semiconductors or transparent materials.
Very nice talk. So you have mentioned that using the ultrafast laser pump and probe to look at the evolution of the defect. I was wondering if you can couple with other techniques to find out the nature of the defect, especially if we're looking at the point defects, so we want to know if it's interstitial or vaguely.
Yeah, that's a good question. Yeah. Yeah, let's do that. What techniques would you use?
Right now, we're also studying the defects, so it's the characterization is very challenging. So one technique we can use to look at the yields, to look at the oxygen LH. That's still not very direct, so we're still trying to look for all the.
Well, so this is for battery applications, is it right? Or?
Not necessarily, just like for metal oxide.
Okay. Well, I'm just thinking that eels is something that you wouldn't necessarily do operando, where you have a device operating. So this might be something that could give you limited information, but you could use it while the device is in operation, and at a later point compare it with something that has a higher fidelity.
Or some synchrotron.
Right. Yeah. That's a good idea.
Do you have that question?
Gotcha.
Just in line with the question,
stuff sliding down the floor.
Right. I warned him about that earlier.
I have a question. The recombination rate that you talked about. So I have two questions. One is that you're going to create a surface transform when you're shooting with laser, which shows the effect of light influence changes the effect of recombination because the electron temperature is not hold at the same interval. But how do you say that if it's smoother, why would you think that the conformation would have any changes?
So you're talking about laser ablation?
Yes.
Oh, so we're well below the laser ablation threshold.
But you still, but you have free electrons that you generate.
Well, these are free, they're in the conduction band, so we refer to them as free electrons.
So you're talking about electron holding.
Yeah. But yeah, if we went to higher fluences, we'd definitely be getting materials in.
So does the energy of the electron change with the influence? That's what you're talking
Well, so the density of the electrons change with the fluence, so the injection density is getting higher and higher. We're pumping more electrons into a smaller space because we're sending in more photons. Yeah.
Questions?
I guess just, you mentioned the gamma darkening of optical fibers. Are folks looking at sonic crystal fibers at all?
You know, they are. The French have done that. They've looked at photonic crystal fibers, and supposedly they have superior characteristics when it comes to rad hard applications.
Would the dispersion or the bandwidth of those be a challenge?
I don't know. One of the guys I work with, Rob Schley, he says they work until suddenly they don't. It's very pronounced. So, you know, for these in-pile questions, maybe working for 10 days is enough. You know, maybe there's, because the fuel changes dramatically when you first turn on the reactor. You get poor redistribution, you get fuel cracking, and so maybe that's long enough. I don't know. Yeah. And you know, and this is for the ATR research reactor. You could go to some of these university research reactors where the neutron fluence is much lower, so the fiber lasts longer.
This is a really elementary question because I'm just learning here. You said you were measuring the corrosion level on the cans. Where's the laser when you're doing that? Is the can actually generating power or whatever it's doing?
So these were proof of principle experiments. So we were doing on a component that had been corroded and autoclaved. So what we're trying to do is sell program managers on actually doing this, because if you did this, you know, in ATR canal, or if you did this in a reactor, we're talking several millions of dollars to do this. But yeah, those are really good questions. Where do you put your optics? How do you deliver your optics? Is that kind of what you're asking?
Well, because my understanding is those cans are in water, right?
Right.
So your laser would have to shoot in water, or actually you have to have something next to the can so you don't have to see the water.
Yeah, well, that's another really important question. So you can pull these out and not look at them in dry storage, but you have at ATR, you have a facility that will go down there after the fuel element's been out long enough. You can go in and locally look at a dry region while the whole thing is still in wire. But so back to your question, doing laser ultrasound in water is difficult. It's not impossible, but the reason it's difficult is that you need to have certain fluence in order to generate ultrasound. And that's really close to the fluence that's required for cavitation. So instead of generating ultrasound in the sample, you're making bubbles. So you have to be careful there. That's a good question.
All right, any other questions? Okay, well, let's thank our speaker one more time.